As far as we can tell, our universe obeys certain rules or laws that dictate how things happen and how systems evolve. It also seems like at the core of these laws are very specific numbers, known as universal constants. These include constants such as Planck's constant, the Boltzmann constant, Newton's gravitational constant, and the speed of light in a vacuum. But what exactly do these constants tell us? What can we learn about the universe simply from the fact that these constants show up in our theories? Put simply, these constants serve as conversion factors. They tell us that two things that we originally assumed to be independent are actually fundamentally linked. As a simple example of this, consider converting between kilometers and meters. Now, we know that there are 1,000 meters in a kilometer, so it's very easy to convert between measurements made in meters and measurements made in kilometers, just by multiplying or dividing by a factor of 1,000 meters per kilometer. We'll give this conversion factor the name A just for simplicity. To see the role that physical constants play, let's assume we had no idea that kilometers and meters were both measurements of distance. Now, say we make a bunch of measurements of the heights of buildings and the distances objects fall when dropped from the same buildings. But we do something dumb. We measure the heights of the building in kilometers and the distances the objects fall in meters. After making all of the measurements, we see a surprising trend. The heights of the buildings are always related to the distances that the objects fall by exactly a factor of A. This constant seems like it's universal, but in reality it's just telling us that meters and kilometers are really just different names we gave to the same thing. In an analogous way, the fact that every inertial observer in special relativity sees light travel the same distance in the same amount of time tells us that space and time are really just two sides of the same coin. The story's the same with, say, mass and energy. In every particle's rest frame, its energy is equal to its mass times a conversion factor, c squared. This happens in other theories as well. For example, in statistical mechanics, a system's temperature is related to its average kinetic energy by some number times Boltzmann's constant. In quantum mechanics, the energy of a harmonic oscillator is just some number times h bar times its angular frequency. Over and over again these relationships turn up, so the question is, if these are just conversion factors, why do we need to keep them around? And the answer is we don't. For example, let's look back at our constant A. If we instead choose to make all of our measurements in terms of, say, meters, the conversion factor between building height and distance fallen just becomes 1, and we can leave it out of our equations. In the same way, if we decide to measure space and time in the same units, as well as mass and energy, and other similar relationships, the conversion factor of the speed of light just becomes 1. We can also do the same thing in other theories as well, just giving us that all of these fundamental constants are 1, and we use some non-conventional dimensions for our other quantities. This system of units is known as natural units. But now that we got rid of our constants, what units should all of the other quantities get? Should time be measured in meters, or should distances be measured in seconds? Well, just like it's up to us to choose whether we want to make our measurements in meters or kilometers, there is no real right answer. So we just need to choose a convention and stick to it. As an example, we can look at quantum field theory, the theory which unites both quantum mechanics and special relativity. We've already seen that special relativity tells us that space and time should have the same units, and similarly for mass and energy. But the addition of quantum mechanics takes it a step further. To see this, let's consider the Heisenberg uncertainty relation between energy and time. Without diving too deep into the relation itself, we can see that on the right-hand side, when we take h bar to 1, we get a dimensionless number. This tells us that the product of energy and time on the left-hand side has to also be dimensionless. So we can conclude that the units of time have to be the inverse of the units of energy. As it turns out, when all is said and done in quantum field theory, every quantity can be expressed in the same units to a different power, typically chosen to be in terms of giga-electron volts, or GeV, where 1 GeV is about the rest mass of a proton or neutron. So energy, mass, and momentum are all measured in GeV, while space and time are measured in GeV to the -1. However, not all theories agree. For instance, in general relativity, we end up with terms that look like this, where m is a mass and r is a distance. Since the 2gm over c squared r term is subtracted from 1, a dimensionless number, this whole term should be dimensionless as well. Now, if we choose our natural units so that g and c are equal to 1, we see that mass and distance have to have the same dimensions. But this contradicts what we found in quantum field theory, where mass and distance have to have inverse dimensions. This is fine as long as the two theories stay separate, but when we try to get the two to play nice together, we have to circumvent this issue. This is typically done by introducing a new constant known as the Planck mass, which is just equal to 1 over square root of g in natural units. When we substitute this into our expression, assuming that the Planck mass has units of mass, then the term we're worried about is dimensionless only if r has the inverse dimensions of m, which agrees with quantum field theory. Okay, so I've talked about what the fundamental constants tell us when they show up in theories, but now let's ask the question that both annoys and intrigues every physicist.
But why?
Why do the constants have the values that they have? Unfortunately, I don't have a satisfying answer. All of these constants are observed quantities, not predicted ones. In other words, we can figure out how far light travels in 1 second by measuring it, and we can say that this measurement should be the same regardless of the inertial frame, but there's nothing in our physics which tells us what values these constants should take. So as of right now, this question is more in the realm of philosophy than physics, but who knows? Maybe one day we'll find a theory which explains the origins of all of the physical constants. But until that day, we'll just have to work with the constants that nature gives us. Thanks for watching, and I hope you enjoyed the video. If you did, then consider helping out the channel by leaving a like or a comment, subscribing, or sharing the video.